DFA that accept set of all strings over sigma equal to a comma b of length 2. Now we will build up on this problem. Now this problem, they very clearly say you should have a length of 2, which means your language, it will be L is equal to, you have a comma b of length 2, okay, and you have AB, which means you'll have AB, then you'll have AA, you'll have BB, and then you'll have BA. It will be a finite language. Now, when we go through the steps, the first step is you will have to construct a skeleton. Okay, so now you construct a skeleton with the smallest string. Okay, I can say the smallest string is AA. So, you know, I'll have this is my initial state. Then I'll be going to a state called B. My input state will be small a. And then after my small a, I need to meet my next state. Okay. So I'll even have a next a. And then that's it. My AA is satisfied. Now let's go for my next string. I'll have to go for AB. A, till here it is fine. Till here it is fine. Next I need a B. Okay, so I can write over here very much A comma B. So A comma B is also satisfied. Next I need to get B, B, which means, you know, very simple. I can write an A comma B over here, and then even my third string is satisfied. The last one is B, A. Okay, so I can travel from A, I encounter a B, I will come to my state B over here, and then I will be encountering an A, I'll encounter an A, and then I will reach my final state C. Now all these 4 strings are satisfied. Now we know how to traverse a string. You start from the initial, then you go through, you go on traversing character by character. If you are able to start from your initial, traverse through everything, traverse through all the inputs, and if you are able to reach a final state, you say that you have a valid string. You say that your string is valid. Okay. So if you are able to start from the initial state, traverse however you want according to your string, and if you are able to reach the final state, you say that your string is valid. Now, when we construct a DFA, not only checking of string validity is enough. We need to do something called language acceptance. Okay, you need to look into something called language acceptance. Now, by language acceptance, you mean 2 things. One is accept all valid strings. Okay. The first thing is all the valid strings should be accepted, which means your DFA which you constructed, the finite automata which you constructed, it should be capable of accepting all valid strings. Okay. Now, if you look here, the only valid strings in this particular language are these 4 strings. You take any of that, my automata will accept it. Okay, so my first condition is satisfied. Okay, accept all the valid strings. Together with that, for a language to be accepted by an automata, you should be doing one more thing. You should be rejecting all invalid strings. All the invalid strings in your automata should be rejected. Okay, so let's talk very simple. Okay, let us think about a string called ABB. Okay, I'm going to talk about a string called ABB. Now look here, ABB, it very much satisfies my sigma equal to AB. Okay, I just have things which consists of A and B. But now look into my next condition. It should be of length 2. But here, it is now of length 3. Now, your automaton should reject it. Okay? The automaton which you constructed just now, you should be able to reject it. Okay? Now, this is an automaton which accepts everything. This is an automaton which satisfies my first condition. Now, my automaton should be modified so that even my second condition should be satisfied. That means all my invalid strings, they should be rejected. Okay, so let's try traversing A, B, B. Okay, so let's start from here. Okay, I'll be starting from here. Okay, so now I'm going to work on A, B, B. I'll start from here. Okay, I encounter an A, so that is satisfied. I encounter an A. I reach B. Now I next need to traverse a small b. I traverse a b. I come over here now in state C. Okay, so now I traveled from A. I encountered a B. Now I encountered a C, and now again I have to encounter another B. I am now in C. As per the string, I have to encounter another B, but my automaton doesn't tell me after my first two characters where should I go. Okay, the automaton which I have constructed just now does not tell me for the third B or for the next B where should I go. Where should I go? Now, in DFA, such things, okay, your invalid things, they are denoted by a state called trap state. They are denoted by a state called trap state. Now, I need to go somewhere. Okay, I am now in state C. I need to go somewhere. So, I will show one more state. I will be showing one more state. I'll simply give it a name called D. You can give it any name. Okay, I just followed D because A, B, C, D. I give it something called D over here. And whenever I encounter not only B, even if my string was A, B, B, A, yeah, or A, B, A, all these are invalid. All these are invalid. Okay, so be it I encountered A or B, the first time I encounter an invalid, which means if I encounter a B over here or I encounter an A over here, my automaton, it will go into a trap state. We call this a trap state. Your automaton is trapped. You can't go anywhere from here. So the moment you reach a trap state, it means you have encountered an invalid string and it should be rejected. Okay, your string should be rejected. Okay, so as of now, this particular automaton which I have drawn will even reject all my invalid strings. How will it reject? The moment you come to a third string, you will go into a trap state denoted by D. So now my language is perfectly accepted. I have accepted all the valid strings and I even reject all the invalid strings. So for this particular problem, what you see over here, this is the DFA. Okay, so that is why in the steps I wrote, you start with your skeleton, you go through all the strings, check whether you will have a trap state or not. How will you check whether you have a trap state? Take any invalid string. Take any invalid string and then make your automata check for the invalid occurrence. Where can your automaton travel? Because even if you have an invalid, your automaton should give you a transition to somewhere. Okay. Anyway, you will reach somewhere over here, and then you should be able to get out of it. Okay. and then fall into a trap state. We'll have the next problem. Construct a DFA that accept a set all strings over sigma AB of length 2. Okay, which means my yeah, this is the problem which we did now. Okay, so we'll go for the next problem. Okay, we did all this. So we'll go for the next problem. Construct a DFA that accept a set of all strings over sigma equal to AB, length is greater than or equal to 2. Okay, length is greater than or equal to 2. So now let's try writing the language. AB, length greater than or equal to 2 means you can have A, B, it goes on and on. Any length greater than 2, which means, you know, it is an infinite language. Your language is now an infinite language. Now, always have in mind, be it a finite language or be it an infinite language, a DFA can be defined. Okay. Now, let's try to build up a DFA over here. Okay. So, as usual, go for the smallest string, AA. So, you know, I'll start over here. A. On the occurrence of a small a, I will be going into my next state. Again, I have a small a occurring. Okay. I will go into my final state. Okay. So, I have done an automaton for AA. AA is now satisfied. Okay. So, let's see AB. AB means, you know, I'll traverse on A. I get a B, then also I will finish. BA, similarly. Okay, I first encounter BA, that is also satisfied. BB is also satisfied. Okay, so my length 2, everything is satisfied. Next, you know, the same thing will occur again. 3 length, 4 length, 5 length, goes on up till n length. Okay, so now look here. 2 you have satisfied. Now for length 3, you can give it like this. So length 2 is over, and then again I encounter an A. Now I'm trying to do an automaton for A. My A is satisfied. I come over here in B. My next A is satisfied. I come in C, and then, you know, my next A, I come back to C. It goes again. It's a cyclic thing. So how many ever, be it 3 length, 4 length, 5 length, n length, be it an A or be it a B, you will be going on satisfying it. You will be going on satisfying it. Okay. Now let's even try drawing the state table for this. Okay. You just have 2 inputs, A and B. You do have 3 states, A, B, C. A is your initial state, C is your final state. Okay, so A on small a, you will reach B. A on small b, you will reach B. B on small a, you will reach C. B on small b, you will reach C. C on small a, you will be reaching C itself. C on small b, you will be reaching C itself. Okay, so this is how you draw a simple automaton. We'll see a few more problems. Okay, so let's have the next one. Length less than or equal to 2. Sigma AB, length less than or equal to 2. Which means, you know, you can very well have your null. Length less than or equal to 2 means you have a null string. Null string is very much possible. So your language will be null string A, B, AA, AB, BA, and BB. Now let's try drawing the automaton for this. Okay, so let's start. We'll have to be a bit careful in this. Okay, I'll start over here. Let's see, A is my initial state. So my smallest string over here is null. Okay, to satisfy null, my initial state itself can be nothing, my final state. Okay, because I am encountering nothing. I am encountering null or nothing, which means to satisfy this particular thing, this particular empty set, I have now made my initial state as the final state itself. So that is satisfied. Now let's satisfy small a. Okay, I go to my next state called B. I encounter an A. That's it. So B is my final state. That's it. So I've satisfied A. Now I need to satisfy B. So I can write either A or B. I reach my final state B. Okay. Next is I need to go for a double length string. What a double length we already saw. You go to a state called C. Okay. And now let's think about rejection. Imagine you have a triple length. You have a triple length string like BBB. Your automata needs to go after encountering the first two things. Where do you need to go? Where do you need to go? So obviously you will go to a trap state. You will be going into a trap state. Be it A or be it B, you will be going onto a trap state. Okay. So let's draw the state transition table for this. How many inputs do you have? You just have two inputs, A and B. How many states do you have? You have states A, B, C. And then D, you can write over here. D is the trap state. Even this line is not there, it isn't a problem. Just write over here. D is a trap state. A is your initial state. A is even your final state. B is also your final state. C is also your final state. Isn't it? And then A on A, where will you reach? A on A, you'll reach on B. B on B, you'll reach on C. Okay? C on anything, it is a final state. There is a chance that you could go into a trap. This is how you draw the state table for this particular automaton. Okay, so always have in mind when you think about a particular limit for the string, like less than or equal to 2 or equal to 2, if the length is specified, okay, you will be having a trap state, because if you imagine of going for a string greater than that length, that should be rejected, which means you are to go to a trap state. That is the simple logic which you can think. Now let's say a small relationship between the string length. Okay. Now we saw that in the first problem, when the length equal to 2, you did have 4 states. Okay. When the length is greater than or equal to 2, you did have 3 states. And when the length is less than or equal to 2, you had 4 states, which means when the length is equal to n, you will be having n plus 2 states. When the length is greater than or equal to n, you will be having n plus 1 states. And when the length is less than or equal to 1, you will be having n plus 2 states. When the length is equal to n or less than or equal to n, you will be having n plus 2 states. When it is greater than or equal to n, you will be having n plus 1 states. We'll go to our next problem, a DFA which accepts a set of all strings over sigma 0, 1, and the string should end with 0. Okay, so they're not telling anything about the length. The only thing is they're telling it should end with 0, which means it will be an infinite language. You can think about 0, 0, 0, 1, 0. Anything which ends in a 0, these are acceptable. Anything which ends in a 1, if it ends in 1, it is rejected. So this is what needs to be done. Okay. So let's think of a very simple. The smallest one, I'll take 0. Okay. So let me construct it for encountering 0. That is satisfied. Okay. Now my next string is 0, 0. Okay. Now I need to think of 0, 0. Okay. 0. I reached over here. I encounter another 0. It should be satisfied. So, I can write over here 0, 0. So 0, 0 is also satisfied. Okay. Now next I want to have 1, 0. Which means, I start over here. I need to get a 1, 0. Okay. So what I can do is, anyway, it should end in 0. It should end in the 0. Okay. So I can think of it like this. 1, 0. Yeah, that is also satisfied. Now let's think of this. 000. Okay, let's see. 0, 0, 0. That is also satisfied. Now let's think of this. 1, 0. Just take any random string. 1, 0. Okay. Here I'm having a problem. Okay. Take this string. 1. 1 means, yeah, I come over here. 0. You know that this string is satisfied, but my DFA doesn't take care of that. So then I'll have to modify my DFA. I've reached over here 1, 0, 1, 0. So can't I do it like this? Yeah. 1, 0, 1, 0. Perfect. Okay. Let's think of any random string, something like this. 1, 0, 1, 1, 1, 0, 1, 1, 0. Any random thing which ends in 0. Let's see if it satisfies. Okay. Let's see if this particular thing is satisfied. Okay. So I go 1, 0, 1, 1, 1, 1, 0, 1, 1, 0. Perfect. Yeah. You think of any random string ending up in 0, it will be satisfied. Let's think of something like this. 111. Okay. So 1, 1, 1. Now I am again A, which means that I don't reach my final state. So this is invalid. If you take any long string which ends up in a 1, it will not be satisfied. So I'll just redraw the thing much more better. So it's something like this. A, B is my final state. 0, 0. I have a 1 over here, and then here 1. So this is my DFA for any string with sigma 0, 1, which ends up with 1. I'll even draw my table for it. How many states do I have? I do have only 2 states. I have an A and a B. A is my initial, B is my final. I do have only 2 inputs, 1 and 0. The columns are my states and the rows are my inputs. So let's check. A on 1. A on 1, you reach A itself. A on 0, you reach B. B on 1, where do you reach? B on 1, you reach A. B on B, where do you reach? Sorry, B on 0, you reach. Yeah. Am I correct? A on 1, I reach an A. Yeah. A on 0, I reach a B. B on 1, I reach an A, and B on 0, I reach a B. Yeah. This is my state transition table. Okay, we'll do one more problem. Okay, so for the next one, construct a DFA over sigma equal to 0, 1, which accepts 1, 0, 1. Okay, so only a single string they accept. they accept only a single string 101. Okay, now always have in mind, when it is equal to or less than, when the language specifies an equal to or a less than. Okay, look here, this is an equal to case, the length. So whenever a language specifies a less than length or an equal to length, there is a possibility of trapping over there. There is a possibility of trapping in equal to and less than cases. Why? Because there is always a possibility you give a greater than case. Okay, so let's try doing this. It's very simple. 101. Okay, so you start at A. You start at A. You encounter a 1. You encounter a 0, and then you encounter a 1. D is your final state. 101. I know there is a case like, you can give a bigger string. You can give a bigger string, A, B, C, D, E. Be it a 1 or be it a 0. There is a chance you might give a bigger string. So, you can say this is the trap state. Similarly, you can even draw a state diagram for them. 0, 1. How many states do you have? A, B, C, D, E, out of which this is your trap. This is your trap. And then you can fill it up. So take down a problem. Sigma equal to AB. Okay, your sigma is equal to AB. And the language will be all strings starting with A. All strings starting with A, which means, you can have A, AB, AA, ABB, BBA, AAA, it goes on and on. It will be infinite. It will be infinite. So let's start with the smallest string. Okay, A is satisfied. A is satisfied. Now you need to satisfy A, B, A, and all that. So, the only thing which you tell is it should start with A, and the remaining whatever, it goes on and on and on. Fine, perfectly fine. But you have not told, okay, look here, there is a possibility of a trap. There is a possibility of a trap. Greater than equal to goes infinite. So always think there is a possibility of a trap. So, you did not tell what happens when you encounter B. When you encounter B, you should be telling what happens. Okay. So when you encounter B, imagine you get a string like B, or you get a string like BB, or BAAA, BAAAB. All these, what should happen? Because, you're told only what happens on A. You have told only what happens in A. If you look into the previous problems, we always say what happens on either A or B or whatever. Here, you did not tell what happens on B. So, when you have B, you will go on a state called C, and then you say it is a trap state. Okay? So, let's see. Encountering B, you come over here. It is not a final state, it's trapped. BB. BB, okay, BB, it's again trapped. BAAA, B, AAA, it goes on here, it doesn't come out. It doesn't reach the final state. It's still in the trap state. Okay, so you can have your diagram accordingly. Okay, you will have just two inputs, A, B. You'll have an A, you'll have a B, you'll have a C, which is a trap. A is your initial state. B is the final state, and then things accordingly. Sigma is 0, 1, and the languages, you should have 3 consecutive zeros. You should have 3 consecutive zeros or ones or whatever. Just complete that problem. So which means, you know, your language can be the smallest string will be 0, 0, 0, 1, 0, 0, 1, 0, 0. You know, it can go into